Welcome to the Explainer. So, if you've ever looked at a massive industrial plant and wondered how on earth do engineers decode the absolute chaos of thousands of valves, motors, and sensors into a clear, manageable framework, well, you're in exactly the right place. Today, we're going to explore how to bring order to all that chaos by mastering sequential function charts, or SFCs, in Somatic PCS7. Let's dive right in.
Okay, let's dive into this bottom-up roadmap. First, we'll look at the blueprint of sequential logic. Second, the anatomy of steps and transitions. Third, mastering operating state logic. Fourth, the Pcs7 engineer toolkit. Fifth, a reactor case study application. And finally, number 6, scaling and handling interruptions.
All right, moving into section 1, blueprint of sequential logic, creating visual order.
So, every automation engineer faces this really fundamental problem, right? How do you manage complex, step-by-step industrial processes without creating an unreadable, tangled web of code? The answer is the sequential control system. You can kind of think of this as the master conductor. It's essentially a step-by-step sequencer that selectively executes automation functions based on operating state changes. So instead of everything just running all at once, it dictates exactly when the underlying continuous function chart, or CFC blocks, should actually do their thing.
I found it absolutely fascinating to see what that looks like conceptually. This visual blueprint? It's literally the ultimate organizational tool for engineers and technicians out there. It takes all that abstract code and turns it into a clear, top-down flowchart that immediately communicates exactly what a process is doing at any given moment.
And this brilliantly illustrates just how flexible that structure actually is. Because, plant processes aren't always just a simple straight line, right? Here we can see some really complex branching logic. You've got simultaneous branches to synchronize parallel tasks, alternative branches based on which condition hits first, and of course, loops or jumps for repeated processing. It's like a giant logic puzzle, but visually intuitive.
But you might be wondering, just how complex can one single chart get? Well, wrap your head around this. A single chart can house up to 255 individual steps and 254 transitions. That means even the most immense, intricate process complexities can be handled super efficiently within just one single visual framework. It's massive.
Let's move to section 2 and see how this builds from the atomic units. Anatomy of steps and transitions.
Okay, so how does this build from that macro chart view we just saw down into the micro building blocks? What we are looking at here is the step phase matrix execution cycle, basically the heartbeat of the sequence. Notice the timeline here. You've got the step active state turning on, then the cyclic execution pulses firing beneath it, and finally the transition condition being completely met right at the end.
Dynamically, every single step breaks down into these 3 phases. First, initialization, which executes exactly once upon entering, then processing, which executes cyclically, and finally termination, which executes just one last time. Now, what's really brilliant about this is that PCS7 strictly limits you to 50 instructions per step. And that's not a bug, it's a feature. It purposefully forces you to engineer with a really clean, modular design rather than, just cramming everything into one messy block.
Once a step finishes up, it hits a transition. Transitions act as the feedback gate to actually advance the sequence forward. But, just like the steps, they have hard limits too. They're strictly capped at 16 logical conditions. This keeps your logic tight, predictable, and honestly, incredibly easy to troubleshoot when a sequence inevitably gets stuck waiting for a specific temperature or pressure to hit.
Section 3, mastering operating state logic, the behavioral rules.
Now that we've got our steps and transitions down, we really need to understand the rules that govern how sequencers actually run, pause, and stop. Notice the flow in this sequencer operating state logic, or OSL, diagram. I know it looks a bit complex, but there is one core rule you absolutely must remember here. Sequencer OSL is entirely subordinate to the overall SFC OSL. So this means an entire chart could technically be in a holding state while its individual holding sequencer is actually in run mode, meaning it's actively processing the specific safety steps required during that hold.
So what exactly causes these states to change in the first place? Well, there are 4 main triggers to keep an eye on. You've got operator commands, like start or hold, external signals coming from other automated systems, internal signals from test modes, and implicit status changes, like when a sequence just naturally finishes. So the crucial point is that these 4 triggers totally govern all your safety interlocks.
To manage all those different states, man, I was amazed to learn that Pcs7 lets you manage up to 8 separate sequencers within a single SFC. It's like having a whole team working for you. You can have one dedicated sequencer just for run, another purely for holding, and yet another just for resuming. They all basically wait in the wings and only execute when the overarching SFC enters their respective operating state. It's incredibly powerful.
All right, Section 4, the PCS7 Engineer Toolkit, Speed and Efficiency.
Let's pick up the pace a bit and focus on the actual user interface tools that save integrators a massive amount of time. Connecting your logic steps to physical plant tags used to be this incredibly slow, manual 4-step selection process in the old browse dialog. Total headache. Now, Method B offers a fast, highly visual drag-and-drop workflow. You just arrange your CFC and SFC windows side by side and literally drag the connection over. Oh, and here's a pro tip for you. Holding the Alt key while dragging lets you effortlessly move existing interconnections around. Real game changer.
Now, what's really interesting about this slide is the calculation dialog. In the past, if you needed to do some simple math, like say subtracting 10 degrees from a baseline temperature before triggering a transition, you had to build all these messy external calculation blocks. Well, not anymore. Inline calculations let you perform mathematical operations directly inside the SFC. It keeps your entire workspace incredibly clean and perfectly contained.
Section 5, Reactor Case Study Application. Theory to Practice.
All right, it is time for the boss fight of this explainer. We are going to take all the abstract rules we've just learned and apply them directly to a real-world plant scenario. This right here is the schematic for the R310 reactor. Over on the left, we have the overarching automation mode blocks, like ModliUp. And down on the actual plant floor, we have specific hardware, like the dosing valves labeled YS211 at the top and the main temperature controller mapped as TICA315. This is the actual physical reality that our logic has to control.
And here is exactly how we bridge that gap. This functional step sequencer for dosing material 1 connects that abstract chart directly to the plant floor reality. Just look at the dosing 1 step. It physically sends a command to open that exact YS211 valve. The valve simply stays open until the next transition, level 1, checks the ALI 214 sensor, and confirms the 50 kilogram level is actually met. Only then does the sequence proceed to close the valve. It is a perfect visual mapping of logic directly to physical action.
Finally, Section 6, Scaling and Handling Interruptions, Engineering for Safety.
So, you might be asking, how do we take a functional sequence, like our dosing example, and rapidly scale it across an entire plant? Well, it's incredibly fast, thanks to a super simple 4-step replication workflow. First, you just select and copy the sequence steps with Ctrl+C. Second, you paste it right onto a free area of the chart. Third, the software automatically increments the names, so dosing 1 instantly becomes dosing 2. And fourth, you manually adapt the specific hardware tags. It literally turns hours and hours of repetitive coding into mere minutes.
But, as we all know, speed means absolutely nothing without safety. What happens if an operator suddenly hits hold during a process? Notice the critical safety mechanism here that utilizes the recomp memory buffer. When a hold is commanded, the current states of all valves are safely saved to this buffer, and the plant actuators are forced into a safe, closed state. Then, when resume is commanded, those temporarily stored values are written right back to the plant. It's a lifesaver.
Which brings us to a crucial final thought for you to take away today. What actually happens to a physical valve if a sudden hold command is executed right in the middle of an active dosing step, and you haven't explicitly configured that protective hold sequencer we just talked about? Well, the sobering operational truth is this. The sequencer holds, yes, but the physical valve remains open, and the material just continues to flow right into your reactor. No way, right? It is a stark reminder that in industrial automation, perfectly structured logic isn't just about efficiency. It is literally the very foundation of plant safety. Thank you so much for joining me for this explainer, and keep engineering safely out there.